This is a video about how to make a simple drum machine with C++ live coding using CPP Sketch. So first of all, you need to go to github.com/elfaudio/CPP Sketch and get the URL to clone the repository. So if we go git clone and then paste that URL and then cd into it, CPP Sketch, and then you need to get the additional submodules. So the way you do that is git submodule init and git submodule update. Yeah, what we're going to do is do this in the sort of audio example. There's a really simple audio example that we can use as a starting point, which is in examples audio. So first of all, you have to make it, type make. So now that's built, and if we look at the code, I use Sublime Text, so I can just type subl and then my live audio. So here is the code. Whoops, yeah, there. It's a simple example. It's sort of hard to read, but it basically makes a rising sawtooth wave or something. I'm not sure. Let's just run it. So /audio, and then now it's running, and you don't have to stop. Whenever you change stuff in here, it's going to update automatically when you press save. So if I change this LFO number to 0.1 rather than 0.001, it changes it. Okay, so we're basically going to get rid of some of this. So I'm going to put here get sample, and just delete all of this stuff. And we're going to make a function called get sample. And basically what this function is going to do is generate the next sample of audio. So this audio out function just basically asks my program for a buffer of audio, and it goes through the array. The reason it's I times 2 equals samples I times 2 plus 1 is that's the left and right channels, but we're just going to work in mono for now. So basically this code is looping through this buffer of samples, and it's going to basically just keep pulling a sample from get sample every time. So how do we create a rhythm? Obviously it's something that's going to be repeating. I'm just going to get rid of those lines of code. So what we can do is say there's a variable called pos, so for position, and every time we go around this loop to get a new sample, we're going to add 1 to it. So pos ++. Now if pos is bigger than say 7,000, so every 7,000 times this loop happens, every time 7,000 times get sample happens, we can make it a hit, and then obviously we need to reset pos to 0 so it keeps looping round and round. And how do we make a hit? Well, one nice way to do it is to think of it in terms of envelopes. So if we've got an envelope, float env equals 0. So we have this variable which it corresponds to the envelope of the signal. So basically when we hit this beat boundary that's defined by this, we're going to set it to 1, and basically every other time we're going to loop round, we're going to just decrease it by a small amount, so 0.999 let's say. So the first time this goes round it's going to be 0.999, the next time it's going to be 0.997 or something like that, and eventually it's going to decay down to practically 0. And that sort of creates this decay of a sort of like exponential nature, which sounds quite nice for drum machines. So if I just type that, and we're just going to play the envelope out of the speaker, you're going to get a click. Okay, so that's our envelope, but obviously envelopes are made for shaping another sound, so we kind of need a source sound. So very simply we can say sine wave. So sin function is a good thing to use. Just need to include math.h, and obviously sin needs to take a period in here or whatever it is, so we can use pos, and if we use pos it's going to be really high pitched because it moves really quickly, like basically every sample it increments itself. But if we multiply it down to, let's say, 0.1, we get a slightly lower sound. Maybe if we take it down to 0.001, I mean 0.01, yeah, that's right, we're starting to get something that sounds like a bass drum, which sounds a bit more interesting. Now this is great, but you know, rhythms need variation. You know, if it's just gonna play every single beat, it's pretty boring, so we need to make it a bit more interesting. And the way we do this is we need to keep track of which beat we're on. So let's make a variable called beat, and basically every time this comes around we're gonna increment beat, and then make sure it so beat equals beat plus 1, and then we're gonna basically wrap it around to 16 places. So it's going to go from 0 all the way up to 15, and then back to 0, and then all the way up to 15, and just keep looping 0, 1, 2, 3, 4, 5, blah blah blah. So that's what that bit does. And then what we want to do is for each of those beat numbers, we want a decision of whether a beat happens or whether it's a rest. So one sort of interesting way to do that is by using a frac function, which is, it basically takes the fractional value of a floating point number. So if we've got, I'm just going to write the function out and then I'll explain it. So basically this method, if you give it like a number like 6.4, it's going to return 0.4. If you give it 3.3, it's going to return 0.3. So it's just returning that sort of fractional number. It's very, very simple and it's very useful. And the way we can use this is, okay, this is slightly convoluted, but it'll be really useful, is if we make a new number called seed, and this number is basically some sort of arbitrary number that's sort of based on beat, but it doesn't like perfectly line up with it. So this number is going to be, if beat is 0, then we're going to get 4938. If beat is 1, then we get 4938 plus 123. So it's sort of like a bit arbitrary, but not totally. We can use this number to create a sort of another number that the fractional number is not related to very much. So for instance, we can do something like frac seed times some floating point number, and then we can test it. So let's say if this number is smaller than 0.5, then do this bit of code, the envelope. So what it's going to do is, like, half the time, because it's 0.5, the fraction of this seed times the funny number is going to be below 0, and half the time it's going to be above 0. It's kind of like a random number generator, but you always know that it's going to be the same time every time this loop goes around. So if we run that, we get something a bit different. And if we change this number or any of those numbers, we get different rhythms. So that's starting to be a little bit more musical. Maybe there's some other things we can change. Maybe we should think about the frequency. So we know if we change this number, we get different frequencies. So maybe we can modify it. So if I multiply it by, we'll just make a new variable called frec for frequency. Define it up here. Say set it to 1, and we're going to use slightly different technique for this one. We're going to say frec is going to equal 1 plus 3 times the seed, or and we'll mod the seed to 10 because we don't want a really high frequency. So let's try that. Okay, so it's starting to sound a bit more like an old-fashioned drum sound, like drum machine sound. Another thing we can vary is the decay. So as said before, if we change this number, we can get different lengths of decay. If we make it really short. So the sort of like the number of 9s here defines how long the sound is. And another way of representing this 0.999 is saying it's like 1 minus 0.1 or 0.01, 0.001. And an easy way to think about 0.1, 0.001 is simply like 0.1 to the power of whatever you want. So 0.1 to the power of 3 is going to be 0.001. It'll be 0.0001. I didn't. Yeah, you know what I mean. So basically what we can do is use this to calculate what we want as our decay. So if we make another variable, say decay, then change it up here, to add that variable here, decay equals 0.999 as a default value. Whoops. Yes, okay. Maybe every beat we can do the same sort of situation. So decay, and then what I was saying before is 1 minus pow, say 3 plus 2 times frac seed 0.9. So what this is saying is we're going to make a number that's 0.1 1 minus 0.1 to the power of 3 plus between 0 and 2, because this is sort of like a random number generator for 0 to 2 using that frac scheme. So if we try that, so yeah, now we've got sort of variation in decay. And then maybe what would be interesting is to have a sort of frequency decay. So using the same principle, we can sort of modify the frequency. So it gets set initially, but maybe we can multiply it by some value, so it'll go up or go down or something like that. So we'll call that frec decay. So here I'll declare it, frec decay equals 0.999. So just to hear what that sound like, we're getting this really sort of laser beam sort of zap sound. But yeah, we'll do the same thing. We'll vary it per beat. Frec decay equals 1 minus pow 0.1. So same thing. And for this one, I think this sounds pretty good. 4 plus 3 times frac seed 0.6. So these numbers in the brackets with the frac, it doesn't really matter what they are. They can be really sort of arbitrary, but I guess you just don't want them always to be the same as each other. Otherwise, all the variations will happen together. So if we try that, yeah, it's getting some pretty interesting things here. And one thing this doesn't do is it only goes down. So what would be nice is maybe half the time it goes up rather than goes down. So we just need to flip this number. So rather than it going 0.999, it's like 1.0001. So sort of flip it around 1, if that makes sense. And the easiest way to do this is saying, like, if whatever our condition is, frec decay equals 2 minus frec decay. And the condition we're going to give is basically just using our frac thing again. So frac seed times 0. whatever. If that's bigger than 0.5, then flip the frequency so it bends up rather than down. Okay, it's not a very good example. Maybe we just try a different beat. Okay, so you got some going up and some going down. And by the way, if you change this number, it's changing all the ways that all the fracts work. So it's going to change the beat, and basically any number here is going to define a drum beat, which is kind of cool. Okay, so I don't know, set this to 0.1.101. It's pretty cool. Okay, so another thing that drum machines have is noise. So what we're going to do is add a bit of noise to some of the beats and not others. So if we make a variable called noise, and basically every time we get a hit, we're going to work out whether to add noise or not. And an easy way to do that is with the bitwise AND. So if you take seed and say seed and 1, what that's going to do is look at seed and like see if the least significant bit in the number is set. So if it's like the binary number has a 1 at the beginning, then this is going to be true, and if it's going to be 1. And if the binary number is 0, the first binary number is 0, it's going to be 0. So we're going to use that. So say noise equals 0.5 times this value. So basically half the time when the seed has the least significant bit of 1, then noise is going to be 0.5, and otherwise it's going to be 0. So we're going to have either half noise or no noise, and I think that's probably going to be enough. So let's add that noise. So let's make a new variable called out, and we're going to make it equal to all of this stuff. So this is just the oscillator stuff, and we'll multiply out. So we're just basically pulling that variable out. It doesn't make a difference to the sound. And then we need a noise source. Now the easiest way to make a noise source is to use this function called rand. I'm just going to paste this function in because it's easier than typing it. But basically rand is this function that makes a really big random number, and then you mod it by 10,000 and divide it by 5,000, and that'll give you a number between 0 and 2 that's random, and then -1 will just make it -1 to 1, which is our audio range, and it's in the standard lib, not mathlib. So I'm just going to fix that. Okay, just check everything's okay. Yeah, so we've got this rand function. I like putting an F on it because it's clear that it's a float basically. And if we just added it here, you just get random noise for every sample, like all the samples. It's kind of annoying. But what we can do is basically mix it in with the original. So we know we've got that noise variable, but we also want to sort of crossfade it with the original signal. So that'll be 1 minus noise. So now some beats have it, some beats don't have it. So that's cool. And then another interesting thing you can do just to give it like a slightly nicer tonal quality is to put some distortion on, and that's really easy. You can just use this function called tan, and you basically put a number into it and make it really big, and it sort of makes a nice soft clipping distortion. So I'm going to try this. It's kind of nice. Maybe it's a little bit too much. Let's try that. Sounds way too much. Maybe just change the beat as well. That's not a very good beat. Try this one. quite a cool one. I think we'll stick with that. Thanks a lot.